All right, ladies and gentlemen, welcome to trigonometry. This is for mainly the 10th graders that are absent, or anybody else who's absent on Wednesday. It's the last section of the chapter, talking about trigonometry and this thing called a trigonometric identity. And the identities are something that actually come up later on, but it's a nice little thing to review at the end of the chapter because it kind of ties some things together that you've done throughout the chapter. Concepts of Pythagorean theorem with trigonometry. So this first one, I'm just going to give it to you, and you can write it down. And we're going to prove it, and then we'll kind of see where it comes from. And again, I'm just trying to expose you to some things you're going to definitely use in Algebra 2 and in pre-calculus and in any of the math you take beyond. Trig has a lot of applications beyond just basic geometry. So the first thing says, prove that for any acute angle theta, we're using that Greek symbol theta again, that this identity is true. And identity just means that it's in a balanced equation, something equals itself, basically. So if you have the sine of an angle and you divide it by the cosine of an angle, oddly enough, you get the tangent of that same angle. Now, when you first look at that, you go, so what, big deal. Well, I'm not going to talk about where you're going to use this, but I just want you to be familiar with it. We're just going to use it as an opportunity to prove something. So you'll see on your paper it says something like, to prove it, substitute or replace these trigonometric ratios with O, H, and A. And you know O stands for opposite side. You know what the A stands for, and you know what the H stands for. You know A is for adjacent, and H, of course, is your hypotenuse. So we're just going to take this equation with a fraction on one side and then a ratio on the other side and just rearrange it here. So you see I'm doing that down here on the bottom. You know your sine ratio. That's comparing two sides. And I would, if I was in class, I'd say, which two sides is that comparing? And of course, somebody would raise their hand and say, oh, it's opposite over hypotenuse. Do the same thing with each one of these and replace all three. So replace the cosine ratio with adjacent over hypotenuse. And eventually I'm going to do this one. I'm going to wait to do the tangent one. Tangent one you'd replace with opposite over adjacent. I'm going to wait to do that for right now. Because you got to this situation where you have a fraction over a fraction, and your Algebra 1 teacher would be very mad if you left an answer with a fraction over a fraction. It's considered not to be reduced or simplified. So just a quick little review of fractions. Some of you will remember this from Algebra 1. How do you divide fractions? And it's a very messy thing to do, to try to divide fractions. We often say, don't divide a fraction. Keep the first one. Keep the top fraction. Change the division to multiplication. Keep, change, some of you remember flip. Flip around the bottom one. So keep, change, and flip. Keep, change a multiplication problem and flip this. And the reason we do that in Algebra 1 is it's so much easier to multiply fractions. You know, this is an easy problem, and as soon as you see it like this, you might not have seen here that this simplifies. I think you can all see that simplifies. Probably obvious to many of you. You can cancel out the h's, you can cross-cancel the hypotenuses, and take a look at what you're left with. You have, if you multiply across here, you have the opposite over the adjacent. And that was just simplifying some messy fractions. And of course, you know that the opposite over the adjacent, you know which trig ratio that is. Which trig ratio is that? Well, that's the tangent ratio. So we just sort of arrived at opposite over adjacent. If I were to take this and plug it in, we'd get opposite over adjacent equals opposite over adjacent. We get something equal to itself. That's what the identity property is saying. Like I said, I'm not talking about where this is used, just kind of showing you an application of trigonometry, something you're going to have to be familiar with later on. I'm just going to do one more, identity. So again, I'll give it to you, and you wouldn't be expected to know where this came from. We're going to prove that it actually works. So again, any acute angle, theta, if you square the sine of that angle, so you type in sine 25 degrees and you hit squared, you get some crazy decimal. You add that decimal to some other crazy decimal, cosine of some angle, cosine of 25 degrees, cosine of the same angle, and you square it, and you get some even messier decimal. If you add these two decimals together, you always get some number. It'd be a good time actually to pause this thing and just try it. You know, type in sine of 25 degrees, square that number, plus cosine of 25 degrees, and make sure you square this number, and add those squares together. And when I come back for the second part, you should have a number right here. Cosine of some angle squared plus sine of some angle squared. And it doesn't matter what angle you pick, any acute angle you want. You want to go 89 degrees, use 89 degrees. You want to go 2 degrees, use 2 degrees. But you got to square them and then add them, and you'll always get a number here on this side. Again, I'll be back in part 2 to talk about that.